What you're about to see is not just a construction project. It's the birth of something that doesn't feel like it belongs on Earth. A dome house rising from nothing, built step by step, piece by piece, into a structure that feels more like the future than the present. And today, you'll witness the entire transformation, from bare ground to the exact moment the dome seals itself into a complete living space. No shortcuts, no skips, just the full journey. So let's begin. The project begins with a step that seems simple, yet defines the entire structure's longevity. The ground is precisely leveled, not just for convenience, but to ensure even load distribution, critical for a dome structure, where forces don't travel vertically, but spread along a curved geometry. Next, the drainage system is installed before the foundation is poured. Often overlooked, but in reality, managing groundwater and rain runoff is what protects a foundation over the next 10 to 20 years. Pre-formed footing cavities are left in place, allowing the concrete to lock in during the pour. Given the lightweight nature of the structure, no steel reinforcement is used in these footings. Instead, stability relies on the mass and density of the concrete itself, a valid approach when soil conditions are stable. Finally, the concrete is poured in a continuous process, no cold joints. This ensures the foundation behaves as a single unit, resisting settlement, distributing loads, and preparing for the dome frame above. A clean foundation, backed by precise engineering decisions. While the foundation is carrying, the crew doesn't stay idle. They begin casting bricks right on site. This is not about saving cost, but about controlling quality. A custom cement sand mix is prepared, not too dry to avoid voids, not too wet to maintain compressive strength. The mixture is then poured into steel molds coated with release oil, producing highly uniform bricks. For a dome structure, this isn't optional, it's critical. Each brick must be consistent in size so the mortar joints remain tight. Only then can compressive forces flow evenly along the curved surface, as intended in dome mechanics. These cast bricks offer high density, strong bonding, and excellent water resistance. More importantly, they provide thermal insulation, an advantage for off-grid living. But this comes at a cost: craftsmanship. Dome brickwork demands skilled labor. Temporary centering, usually wood or steel formwork, is required to support each course until the mortar fully cures. A slight misalignment can compromise the entire geometry of the dome. With the foundation set and materials prepared, the structure begins to rise. The first curved frame is erected. This is the backbone of the entire dome. At this stage, precision is no longer measured in centimeters, but in exact angles and elevations. Steel pipes are bent to match the designed radius. Any deviation will disrupt load distribution, potentially leading to deformation or structural cracks over time. Wooden battens are then bolted onto the steel frame. They don't just add rigidity, they provide a stable interface for the outer layers. Next, thin plywood sheets are applied over the curved surface. This step defines the geometry, transforming segmented arcs into a continuous shell, ready for brick and mortar application. At this point, cumulative error becomes the biggest threat. A slight misalignment at the base will amplify toward the apex. This first frame doesn't just stand, it sets the standard for the entire structure. At this stage, the structure is not yet a complete dome. They are working on individual curved frames, turning steel skeletons into independent structural modules. The precast mortar bricks, now fully cured, are brought into place. Thanks to their uniformity, the bricks fit precisely along the curved surfaces, minimizing gaps and reducing joint inconsistencies. Earlier, the curved frames were covered with a layer of steel mesh. This mesh provides mechanical grip for the mortar. A thin coat of mortar is then applied, acting as a bonding layer between the frame and the bricks,
while also forming a stable surface once the temporary supports are removed. Here, bricklaying does not follow a radial pattern. Instead, it follows the geometry of each curved frame. At this point, loads are still transferred through the temporary structure, not yet fully self-supporting. Once the surface is fully covered, a second layer of steel mesh is added externally. This reinforcement layer binds the system together, reducing the risk of delamination and surface cracking. At this moment, the structure is still preparing to carry its own load. Once the curved structures have fully hardened, the temporary frames are removed. This is the true moment of verification. If the brick and mortar system has been executed correctly, the structure will stand on its own, without support. The frames are dismantled gradually in a controlled sequence. No sudden movements, no full removal at once, avoiding shock loads on a system that is still stabilizing. As the supports come off, minor imperfections appear along the edges. Excess brick sections are trimmed, not just for aesthetics, but to eliminate stress concentration points. The cut edges are then finished with a layer of mortar. This acts as an edge lock, sealing gaps, improving cohesion, and preparing clean boundaries for the next stage of assembly. At this point, the structure transitions from temporary dependence to partial self-support, a process of removal that ultimately confirms the integrity of everything built before. This is the most demanding phase, where true craftsmanship defines the outcome. The central dome is now being built, without major support frames, relying purely on geometry and skill. Each brick is placed radially, angled toward the apex. Unlike standard wall construction, there is no vertical support. Gravity constantly pulls each brick outward. This is the core challenge. To counter this, builders use tension guidelines anchored from the base of the dome, pulling against gravity. These lines don't lift the bricks, they prevent them from slipping before the mortar gains strength. At the same time, they help control the precise placement angle along the compression path. Mortar consistency is critical, firm enough to hold position, yet workable enough to allow adjustments. When the final keystone is set, the dome transitions into a fully self-locking structure. A system working purely in compression, yet capable of forming a strong, open, and enduring living space. Once the central dome is fully self-supporting, they begin modifying the structure, a step that leaves no room for error. A large window opening is cut directly into the dome wall. This is not just about creating space, it's about redistributing structural forces. Every cut must be calculated to avoid interrupting the continuous compression flow within the dome. To compensate for the removed material, a new curved frame is installed within the opening. Its geometry is not arbitrary. It must match the dome's radius and curvature, allowing forces to be redirected smoothly to both sides. Bricks are then laid to form a smaller arch around the opening. This creates a dome within a dome, a classic structural solution that channels loads away from the void rather than letting them collapse inward. The real skill here isn't in cutting the opening, but in ensuring the structure behaves as if it was never interrupted. A well-executed opening doesn't weaken the dome, it completes both its function and its form.
With the entire structure completed, the process shifts to refinement, where construction quality becomes truly visible. Excess materials are trimmed away, not just for aesthetics, but to eliminate potential stress points in areas where moisture could accumulate over time. The central dome surface is reinforced with a layer of steel mesh, followed by a finishing coat of mortar. This mesh acts as a bonding skeleton, helping the mortar adhere firmly while reducing cracks caused by shrinkage and thermal movement. At critical junctions, such as window frames, reinforcement is applied more carefully. These areas are prone to cracking due to material differences and movement. Additional mesh and mortar layers help distribute stress and maintain long-term stability. Inside, surfaces are smoothed to improve usability and to enhance light reflection within the curbed space. This stage doesn't change the structure, but it defines durability and user experience for years to come. A well-executed finish is the final layer of protection for the entire build.
With the primary structure complete, the project shifts into spatial organization. The main entrance is defined by two low brick walls on each side, forming secondary openings, while the central gap serves as the main doorway. This layout not only guides movement, but also helps distribute loads above, avoiding concentration over a single large opening. A wooden door frame is then installed at the center. Here, wood is not just a finishing material, it acts as a buffer, absorbing minor movements and reducing cracking risks at the junction between rigid structure and openings. Inside, the bathroom area is handled differently. A wooden frame is first erected, defining the space and acting as a structural guide. Bricks are then built around it, forming an enclosed shell. This approach isolates moisture-prone areas while ensuring loads are not directly transferred to the main dome structure. At this stage, the building is no longer just stable, it begins to function as a livable space. With the spatial layout defined, the technical systems are installed, embedded within the structure. Electrical wiring is laid before interior plastering.
The cables follow the curvature of the dome walls, minimizing sharp bends, reducing wear, and improving long-term safety. The central electrical panel is positioned for easy access and control. Outlet and switch points are pre-marked with precision. Once the final plaster layer is applied, adjustments become extremely difficult. At the same time, the plumbing system in the bathroom is installed. Pipes are concealed within the structure, with carefully calculated slopes to ensure proper drainage, preventing water stagnation and backflow odors. After completing these systems, the bathroom is finished with a plaster layer. This not only creates a usable surface, but also protects the internal systems from moisture and mechanical impact. At this stage, the project completes its hidden infrastructure, elements that remain unseen yet define the building's long-term performance. With all internal systems completed, attention returns to the outer shell. An additional finishing layer of mortar is applied to the exterior of the dome. This is not just for appearance, it acts as the final protective skin of the structure. The surface is smoothed carefully and evenly, reducing water retention and improving resistance to moisture penetration. In a dome structure, rainwater flows along the curved surface. When properly finished, it runs off continuously without pooling. This layer also seals micropores from previous coats, minimizing water ingress and improving durability against weather exposure. Thickness control is critical. Too thick, and shrinkage cracks may develop. Too thin, and protection becomes insufficient. This is a stage where craftsmanship matters more than tools. A seemingly simple layer that ultimately defines how well the structure withstands time and environment. With the finishing layers stabilized, the project enters its final installation phase. Lighting fixtures are installed first. In a domed space, lighting is not just functional, it must be distributed carefully, using the curved geometry to minimize dark zones. Window openings are fitted with glass. This step completes the sealed envelope, protecting against wind, rain, and stabilizing the internal environment. Due to the curved surfaces, precise alignment is critical to avoid gaps. In the bathroom, sanitary fixtures are installed in coordination with the pre-laid plumbing system. Every connection must be fully sealed, as post-installation repairs can be difficult. Finally, the bathroom surfaces are tiled. These tiles serve not only aesthetic purposes, but also act as a primary waterproofing layer, protecting the structure from long-term moisture exposure. At this stage, the structure is complete, both technically and functionally ready for use. The air conditioning unit is installed in its designated position. Outside, trenches are dug to route the main electrical supply. Cables are buried underground, not only for mechanical protection, but also for safety under varying weather conditions. The connection from the power grid is fed into the central electrical panel, completing the building's power system. At this point, all connections must be fully insulated and moisture protected. This is the core of the entire electrical network. All interior and exterior surfaces are painted white, not just for a clean and spacious look, but for clear technical reasons. White has a high thermal reflectance. On the exterior, it reduces solar heat absorption, helping keep the building envelope cooler under direct sunlight. Inside, the white surface enhances light reflection, allowing the dome space to be evenly lit with fewer artificial sources. The paint also acts as a protective coating, reducing surface moisture absorption, limiting dirt buildup, and extending the lifespan of the underlying plaster. In a dome structure where surface exposure is significant, color choice is not just aesthetic, it's part of the energy efficiency strategy. A well-applied coat completes both the function and durability of the entire build. With the outer shell complete, the living space is finally activated. The floor is coated with epoxy, creating a seamless, joint-free surface. Epoxy offers strong waterproofing, easy maintenance, and high wear resistance, ideal for continuous living spaces like a dome house. This finish also enhances light reflection, working with the white interior to make the space feel larger and cleaner than its actual size. The kitchen area is completed with a fixed countertop. Materials here must withstand heat, moisture, and impact, requiring careful sealing at all joints to prevent long-term water damage. The resting area is arranged with a bed and sofa. In dome architecture, furniture placement is not just about comfort, it must respect the curved geometry to avoid visual clutter and wasted space. At this stage, the structure is no longer just a build. It has become a complete living environment, ready for daily use, function, and experience. And now, the final moment. The transformation is complete, from nothing to something extraordinary. Not just built, but shaped with intention, with precision, with mastery. This isn't just construction, it's the meeting point between human effort and the raw logic of nature. Every step you've seen, every layer, every detail was part of something bigger. And now, it stands finished. A dome house, ready to be lived in, ready for the future. And this was the journey, from the first layer to the final form. Thanks for being part of it. We'll see you in the next incredible build.